So first of all, we talk about simplify assumptions. So if we use all the equations that we have, the equations would be really complicated and we will use a lot of computer resources to solve the equations. So a very, very simple trick that we can use is that we can do scale analysis, and then we can eliminate the smaller terms in the equation before we do any kind of calculation. And then we will reach a solution where we get rid of some unwanted signals, for example, sound waves. When we do that, there will be cost. The cost would be some errors happening in our solutions, but it would be worth it because we would save some computational power. Okay, so this is a I think you all have seen the different scales in the atmosphere, but if we put that in a speed perspective or velocity perspectives, we have the spatial scales in x-axis, and then we have the time scale in the y-axis. And if we put all the weather systems in this graph, they would be pretty much lying in between, okay, in here. So these are the stuff that we want in the solutions from our atmospheric models. And these are the things that we don't want. For example, acoustic waves, sound waves. Okay, they're much faster. They're not wanted. They're not the weather systems that we want. Okay, and then another type would be really slow. The spatial scale is really small. And then they last for a very long time. These are the things that we don't want because we already know that they're there. It's not that they're not important. It's just because we already know that they're there. And these are the things that we don't know most of the times. Okay? Okay, so the first step, a very simple trick, would be to eliminate the sound waves in our solutions or in our equations first. So we expect wave-like solutions in our system of equations. And the first step would be to do filtering approximation. Okay, so the simplest form probably is to assume that the atmosphere is incompressible, which comes at a cost. And then the second type would be an elastic approximation. We will get into this now. Okay. So last time we talked about this. So this is the original continuity equation on the right. And we assume that following the air motion, the density rho here doesn't change. So that's why we arrive at this incompressible atmosphere in here. Okay, we don't need the information of density anymore. We just need the information of the speed. Okay, this is the incompressible atmosphere. Okay, there are three criteria that we need. The first one is that the motion that we want, remember the graph, the spatial, this one, okay? So the speed of the weather systems, or the general speed of the weather systems that we want, is not the same as the speeds of the sound waves. It should be much smaller, okay? This is the first criterion. And then the second one is that the time scale for the change in density, so this is the time scale for the change in density, should be much larger than the time scales change due to sound wave propagation. Also, you can think of it as the period of sound waves. So the period of the change in density due to the air motion should be much larger than the time scale of sound waves. Okay. And then another one, which you are probably very familiar, is that the vertical scale of the circulation should be much smaller than. the horizontal scale. Oh, sorry, much smaller than the scale height of the atmosphere. So it should be a shallow layer of air motion. Okay, so whenever you see a star here, I'll be writing something, and then you will have to write it down. Okay, I'll explain a little bit on this scale analysis here. If you can't see it, please tell me, okay? So we will be doing scale analysis on the momentum equation. We have three momentum equations. The first two they're responsible for horizontal, and then this one is vertical. And we can combine them into a vector form. We'll perform scale analysis on this one. So the transformation of these equations into the vector form is in here. I'm not going into details. You should know about this already, right? It's for your information. It's not going to be in the exam, okay? Okay, I will rewrite the vector form of the momentum equation first. This is pressure, okay? And then divergence of the shear potential. Okay, so the third criteria is that your air motion, okay, if this is the height of our atmosphere, and your air motion should be in the very small layer of the atmosphere. Can you see this from the back? Can you see this from the back? Okay, okay. Very small layer. Small vertical scale. Okay. Okay, so this is the horizontal scale, LZ, and then vertical scale is X. Okay, so that's why we are saying that this is smaller than this one. Okay, so first step is that this one is gone. Oh, sorry. This one is gone. Okay. This is the third criteria. Okay, so what about the first and the second? Okay, we know that this part, the first term, the term on the left, the scale of this is v squared, right? V squared. Okay, and then the second part, this is 1 over rho. Rho is the density. And then this one, we need some other physical law to change this into the scale. Cs is the speed of sound waves, and then the change of density due to sound waves. Okay, I have that in the slides. It's for your information, okay? It's for reference. Okay, so the physical meaning of this term is that it's the divergence. You can see this, right? Divergence of the pressure corresponding density variation due to sound waves. Okay, we change that into the divergence of pressure due to sound waves. Okay. So now we can do the scale analysis. We have crossed out the second term on the right. So we have the change of density over density, right? Here and here, the terms on the right. Sorry about this. Okay. Equal to v squared. Okay, so looks like that we can put all the numbers here. We have the number for v, and then we have the number for cs, which is the sound, the speed of sound. It's in the slides. Right, it's in the slide. Okay, it's in slide number 7. So then we can do the scale analysis. So this big O notation, it means order of. It's not O, okay? We know that it's a very, very small number, almost 0. So this O means order of. Okay, what does that mean? It means that now we know that this is very, very small, which means that we know the density change with respect to the density is very, very small, okay? Which means that we can, if it's a shallow layer air motion, we can ignore the density variation, which means that we can think of the atmosphere as an incompressible fluid, okay? Okay, so it means that if we do the total derivative of density, the change, this approximation is appropriate if the 3 conditions are fulfilled. Okay, this is how we can eliminate terms. Okay, this is for your reference. If you want to know more about the math, you can read Houghton. I also put the link here. Okay, so next, what if we want some type of variation in our atmosphere, density variation? Okay, the next simple model that we can use is called an elastic approximation. So what is an elastic approximation? So the atmosphere will be looking like layers and layers of density. Layers and layers of density, so an elastic approximation. So in this kind of model, we separate the density into, we just express this in one term. So density only depends on height, which means that if you go from one place to another place with the same height, the density would be the same, and then it will not change with time. Okay, so what does it look like? If this is the height, oh sorry, my drawing is. Okay. Okay, it should be straight lines. My drawings are no good. Okay, you can draw the straight lines in your notes. Okay, so density only depends on height. What does it mean? If you use the full continuity equation, you can eliminate some terms, which means that it doesn't change with time, right? And then it doesn't change if you go from one place to another place, right? Horizontal change, also 0. Okay, right? But one thing that is not 0 is that if you, this is not 0, right? Which means that these dimensions, they don't matter. Okay. Okay, if we go back to the continuity equation, and we know that the first term, it's 0 because of here, right? First term is 0. And then we can expand the second term. Replace the row with row naught. Sorry, here it should be all row naught, okay? Or row, doesn't matter, it's the same. Okay, and then what do we have? Okay, you can refer to what we have written on the right. We have crossed out some terms. Okay, that's why we arrived at the equation that, okay, this is how we arrive at this equation. So for the horizontal flow, it's always incompressible. It's more realistic because the atmosphere, I mean, the density should be decreasing when you go higher, right? It also doesn't allow sound waves because the density doesn't change with time, even though you have different layers of density in the atmosphere. Okay, for the vertical flow, it would be more realistic because the density decreases with height. Okay, so next is that we want to look at the equation that we have just developed, if it's realistic when it's a real situation. So here we are trying to do scale analysis for synoptic scale motions. So if you forget what is synoptic scale motions, I have a slide here. This is synoptic scale motion. We even have length. So around 2,000 kilometers air motion, anything smaller than that, the inelastic approximation doesn't apply, okay? Which means that if we have, for example, frontal rings or thunderstorms or small scale turbulence, they don't work, okay? Why do the textbooks always mention synoptic scale motions? Here, this one. In all the American textbooks. Because for the synoptic scale motion, the geostrophic flow approximation, we can apply that. Okay, most of the times it is correct. And then when they do simulation, it will be easier because they have eliminated anything smaller than that, which means that smaller noise in your model when you initiate your model. So that's why, but it only works in the mid-latitude, so it doesn't work in our area. Okay, so the scale analysis on the continuity equation. Okay, this time the atmosphere is a little bit more complicated. Okay, so this time the atmosphere, we also have the rho naught. This is rho naught, which changes with height. We separate the density into two terms. Rho naught plus the density variation. Okay, this one changes with time, it changes with space. So this rho naught doesn't change with time, which means that your model can only handle the rho pi in your mathematical equation. Okay, so this is rho pi. Which is the changing part of your equation. This is a non-changing part. No. Non-changing part. Okay, so this is a very simple technique in atmospheric science. We separate the motions into different scales. Here we separate the density into the non-changing part, which should be a larger number, right? Rho naught. And then rho pi is the changing part. It's a smaller scale oscillation in the atmosphere. Okay, some of the models, they only handle the second part because the first part doesn't change with time. So you don't need that representation in your model. Okay, so what does that mean? It means that we know that, sorry, this is not 0, right? This is not 0, okay, the oscillation. Okay, so now we can work on the continuity equation. Continuity equation. Okay, so this is the same expression as the continuity equation, which is the same as this one, okay? Last time we talked about how we can interchange these two. Okay, it's exactly the same thing. And then what we want to do is that we want to put rho naught plus rho pi in all the terms here. Substitute this into the equation. Oh, sorry.漏咗一樣嘢喎，好似，漏咗個rho naught，sorry。漏咗個 term, okay, I've missed this term inside the bracket. Okay, so then we will arrive what we have in the slides. Okay, so I think we have combined the terms. Okay, so this bracket comes from here, I think, and then this last term is this term. Okay, we have arrived this. So why do we do this? We want to rearrange the terms so that we can do the scale analysis. So this is the scale analysis for synoptic scale motions only. Okay, the first term, because the rho naught is very small. If you look at this scale, it's 10 to the power of minus 7, which is one order smaller than these two. So if we do calculation, they dominate all the motions, which is that one, okay? If you're fast in math, you know that it's exactly that one. What does that mean? Why are we doing this? Okay, I'm not going to write this. So even if you introduce rho naught in our equations, we have introduced this one, right? Comparing to the last model. Even if you introduce this one and then we do scale analysis, they will still be gone. Okay, this one is still gone. Which means that the inelastic model still works for synoptic scale motion. Okay, so for the inelastic model, what does that look like? It looks like this one, right? This one. Okay. So you think that it's a very simple model, then it might not work most of the times, right? But it's not true. If you just look at synoptic scale motion, even if you introduce this rho pi here, they would still be gone, which means that you don't need this. Okay, you only need that for synoptic scale motions. Okay, so this is the rationale behind the scale analysis. Okay, so I have put up a simple schematic diagram for you. So if you are looking at the shallow layer of motion, you can just use this incompressible model. So if it's higher up, if it's a thicker layer, then you can use an elastic model in which we only have layers of different densities. They don't change with time. Okay, and sound waves are still excluded in this situation because we don't have rho pi. Okay, so next is I think everybody here knows about this hydrostatic approximation, but there is a little bit more into it actually. So when okay, I will go to this. So what does it look like? The original vertical momentum equation. For hydrostatic approximation. The original vertical momentum equation looks like this one. I know you forgot everything already, right? From 2020 and then 3200. That's why I'm rewriting this. If you're bored, you are free to go. Okay, so from the scale analysis, we know that these terms are gone. Okay, so that's why we are saying that the atmosphere, its hydrostatic balance for larger scale motions. We crossed out them also for synoptic scale motions because all the textbooks, they are focusing on synoptic scale motions. So for anything smaller than that, this doesn't work. Okay, so this is how we arrive at this. Okay, if we separate the pressure again into two terms, again, oh sorry, P. 負啊係留有個負啊So we separate pressure into two terms again. It's the same operation for density. We substitute this to your okay. So for scale analysis, we have already proved that this P naught should be in hydrostatic balance with this rho naught. And another thing we need to prove is that if this P prime is in hydrostatic balance with the rho pi, if you want to introduce this rho pi, you need to take care of the P prime pi too. Okay. We have to do this. We have to prove this because P prime also will appear in the horizontal momentum equation. Okay. That's why we need to prove that. I'm not going to do this proof. If you're interested, you can read this. This is beyond the scope of this course. Okay, I have put that in the slide, I think. Yeah, Houghton. Okay, we call this dynamic pressure. So this is only applicable if your horizontal scale is much larger than the vertical scale, which is the same situation as this one. Sorry, this one. Okay. Okay, so next we talk about another type of approximation. I think you probably have heard of it, the Boussinesq approximation. For this approximation, we separate the pressure and density into two terms, the non-changing part and the changing part. And then this approximation is a little bit different from the models that we have just discussed, because this approximation, we also deal with the momentum equation. So for all the models, the incompressible, the inelastic model, we only talk about continuity equation. For this kind of approximation, we directly assume that the fluid is incompressible. But the trick is that we keep the rho pi, or this rho slide thing here, the changing part in the momentum equation, in the vertical momentum equation, when it's dealing with dense gravity. Why do we keep that if it's related to gravity? Because gravity is a large term. Gravity is around 10, right? The order of gravity, comparing to all other terms. Even if this number is very small, when you multiply that with gravity, it will be huge. Okay, that's why we keep that in the vertical momentum equation. Okay. So I have put all the math in the slides, so I can draw you a simple graph for this. So when does it work, this Booth-Ness approximation? It also works for shallow layer because you already assume that it's incompressible, right? We assume that rho equals to rho naught everywhere. Incompressible. Dealing with gravity. Since G is a large term. Right? So in here, sorry. So inside this layer, if we have an air parcel going up, so this is dealing with gravity, so I have to talk about buoyancy here. If we have air going up, okay, this is our atmosphere, the Booth-Ness approximation, right? And then this is the bubble that we have here. Okay, if I think you know about buoyancy, right? In your physics course. This is the air. If you don't replace this part of the atmosphere, so this is air and then this is air, right? So your air here, what is the buoyancy force? It should be given by, it should be the related to the pressure of the air here, right? But it's the same air. So the buoyancy force should be given by the force that your air is originally given inside this space. And if you replace that, it will still be the same buoyancy force. Sorry, this is P naught, and then outside also P naught. So the buoyancy force which are the arrows. Okay, so if you replace this it'll still be the same buoyancy force, right? But we have to do something to the equation. Okay, these are the arrows. And then this one is what we call perturbation, which is coming from the changing part of the pressure. Okay, so this is why we have to rewrite the equation. I have the math in the slides, I think. Oh. In here, this is how we rewrite the gravity, adjusted gravity. So this is due to the density variation in our atmosphere. So if there is no variation, then you don't need this term, right? Okay, so I have put up a table, sort of a table for you to understand how we can look at the change of density in different types of models. So the simplest one would be homogeneous density, which is the incompressible fluid. And then here, the second simplest model would be Boussinesq approximation, because it's still incompressible, right, in the continuity equation. But we have density variation in the momentum equation. Okay, this one is pretty special. People use this for the boundary layer. Okay, this is applicable in the boundary layer. Okay, and then this one is inelastic, which is a little bit more complicated than this one, because we allow the density to have different layers. This is more complicated than this one because you can look at this one. Okay, and then fully compressible. Okay, why do we do this? We want to speed up the calculation. This is the sole purpose of doing this. Okay, I think we should take a break. Maybe 5 minutes.